Recording in progress.
Da, 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 da. There. Alrighty, so welcome back, guys. Hopefully you signed in already. Quick note: all lecture slides and recordings are posted on Dav links, and this lecture slides are already posted. So if you want to follow along, you can. Alrighty, so quickly, what are we gonna do today? We're quickly gonna go through some Oh, right, I'm using this one. Right. All right, we're gonna go through some announcements. All my titles are clipped. Whatever. All right, so we're gonna go through some announcements, and then we're gonna do some gate review again. Last time I kind of fucked up the recording. Let me make sure it's good this time. Uh, yeah, it looks good. All right, so just really quickly, and then we're gonna go through some binary, and then combinational logic, and then I'm going to basically run through an entire like system Verilog project, so you guys can see step to step how to do it. Alrighty, so some quick announcements.
Okay. So yeah, as we said last week, this year we had a lot of applications, and so we were able to accept everyone. And we won't be changing this decision. And yeah, again, auditors, you have no access to work sessions, no team assignments, no check-in with leads, no food, and potentially less help with labs, but you are able to show up to lectures and have all of our material.
Yeah, so just a quick reminder on that.
Again, DAV kits will not be allowed to be taken outside of the IEEE lab. This is due to the large amount of DAV members. You are allowed to use it whenever Gerard or I are in the lab for auditors, and then for general DAV members, you can use it whenever the lab is open. And then team and team channels have been made. If you haven't seen any of that, please DM either me or Gerard. And then if you have any questions regarding DAV, please text in the team channels, don't DM us.
Oh, that's you.
Oh, okay. Yeah. So your first assignment was to install Vivado onto your computers, and also complete all of the logistics. If you have a Mac, I linked some stuff on Discord that will hopefully be helpful to you to installing Vivado on a Mac. You have to go through like a VM. I know of someone that has successfully done this, so hopefully you guys don't have any trouble, and come to my lab hours if you need help.
Alrighty, so lab one has been released. This was actually a while ago, but now you guys will actually have the content to be able to do it. So it's time to get to work, y'all. There are a bunch of useful resources in Dav links and on the doc. I try to make it as streamlined as possible. So this lab will hopefully be finished by next lecture, which will be 2 weeks exactly from now, scheduled November 13th. So I'll see you all back here. Yeah. So lab extension policy. So, this is not a graded class, so we're not going to be like, get it in. But this deadline is very, very highly recommended to keep up with Dav. If you don't want these to pile up, and it's fun, so you should do it. So yeah, so just let the leads know ahead of time if you need an extension, and I will be grumpy if you ask questions about labs from a long time ago. So don't do that. Yeah, so our first work session will be held next Wednesday, November 6th, almost certainly here, but could change. This will also be between 6 to 8, and we might have food. So look forward to that. So just so you know, work sessions are basically like large office hours. So you guys will work on your projects. Me and Jonathan will be around to help. So take advantage of this period so you don't have to debug syntax errors for like an hour. And yeah, also our lab hours exist. Come visit if you need to. Yeah, so basically next week we true. Next week we have the work session, and then the week after that is lecture 3. And then, so I did mention with spring quarter we might have some special lectures. I might do a lecture on IPs and UVM, but they're just like useful in actual industry, but they're kind of outside the scope of Dav. So let me know if you actually want to hear that. All right, so quickly we'll go through digital logic review. So I went through this last time, but it was kind of messed up, so I'm going to go through it even faster. So basically, digital logic, we don't like analog things because they're confusing and have infinite values. So instead, we simplify what we have into zeros and ones, so on or off logic. So basically, 0 usually represents a low amount of voltage, usually 0, which means off, and then the 1 represents a higher value. Now, this higher value tends to be 5 volts. I think our FPGA actually uses 3.3, but basically 1 means on, 0 means off. And then, so basically you're able to simplify signals into square waves, which are a lot easier to understand. Okay, also, especially since it's dark, um, if you have a question, feel free to just interrupt, be like, yo, I got a question. Because I will not see your hand. Okay. So yeah, so real quickly, these are the gates. You saw them last time. So if you haven't taken M16 or aren't super familiar with the gates, I'd recommend like having this slide pulled up with all the truth tables, because this is going to be the fundamental building block of all the logic we derive today. And you need to know what do these gates do? So basically, quick explanation is that little table, the ABQ table, is the truth table for each gate. A and B are the inputs, and Q is the output. So for the first table, I put in 0, 0 for A and B, and I get Q out of it. And that's our AND gate, which was not really named. So, whatever, it's fine. Actually, it's not fine. This is AND gate. Mine's my handwriting. This is OR gates. Yeah, so eventually try to memorize these tables, have them down, because
Oops, there's a mistake. There should be 2 1s here.
dude, what the heck did they do last year, bro? Okay, yeah, that's good catch. Let me make sure the other ones are correct as well.
Like 1 and 0.
Oh yeah, true. Okay, good catch. Alrighty. So yes, these are the correct ones. Okay, so take a picture of that. Nor basically means not or. Not is represented by that circle thing at the end. Yeah. So get those truth tables down, guys. NAND, same thing, not and. XOR, what that means is basically exclusively or. Uh, so what that means if it's like pretend this was an OR gate, if this is 1 and is 0, then it's 1. But if and is 1, then it's 0. So that's a quick, easy way to memorize that table. And then there's the not. So not actually only takes 1 input. It reverses it. So you put in 0, you get a 1. If you put in 1, you get a 0. So I went through that super fast. But I have some quick examples to make sure you guys all got this down. So go and give these a try. Raise your hand once you get question 1 and question 2. Or only actually, yeah. Raise your hand if you get question 1. Yeah. What'd you get? 1, yes, that is correct. So I'll quickly go through it. One thing to note is that these filled in dots, these are knots. So sorry, since we started lecture kind of late, I'm zooming through. So yeah. So basically A is 1, B is 0, C is 1, D is 1. Output of here, 1, 0, this is going to be 1. Output here, this is going to be 0. Output here, this is 1. Output here is 0. Now there's this thing called wired OR. I don't like wired ORs. So basically what it's saying is that this means that there's basically a OR gate there. The reason why I don't like it is because, as you can imagine, 1 and 0 actually represent voltages. So as you can see, these two nodes are different voltages. So like that node should be 1 voltage. So it's kind of weird. So yeah, I don't like wired ORs, but I took this off the internet. So just don't do that. Yeah, quickly. So wired OR, so this becomes 1, this becomes 1, 1 and 1, it's 1. So yeah, review that over so that way you can go through it. You don't have to do it that fast, but that's kind of like, you want to be comfortable with these logic gates. Has anybody got question 2? Yeah. I think that is one of the solutions. Yes. Okay, let's do it. So sorry if this is really fast. I did say M16 is a recommended prereq, so it's on you. I'm just kidding. But what the gate is no blah blah. A is 1, B is 0. So our output after this not is going to be 0. Our output here is going to be 1. 1 ANDed with 0 is 0. And then down here, A ANDed with B is going to be this is 1 0, so this is 0. So yeah, I wanted 1. So basically I need to find a truth table that has this equation, and NOR does indeed work. I think XNOR works as well. So yeah, good job, guys. So yeah, if you aren't super comfortable with it, since I zoomed by, just like reviewed a little bit and should be good to go.
Okay. Now we're gonna briefly breeze through binary. Yeah, so as you may have noticed, we really like to use zeros and ones. And computers do as well because of thank you. Yeah, computers do as well. And so we're gonna be using binary, which is like a different number system as what we're usually used to. And so binary is in base 2, so the only two numbers that are possible that you can use to represent digits is either 1 or 0, as opposed to our traditional number system, which is base 10 or decimal. And in addition to that, there's also hexadecimal, which we won't really cover here. But if you're interested, you can search that up. And so here I have 3 examples. One example of like where 25 can be represented as in binary, decimal, and in hexadecimal. Yeah, so how do you actually interpret a binary number? So each one or 0 is a bit. 8 bits make a byte. And each bit represents a power of 2 ascending from the least significant bit to the most significant bit. And so the least significant bit is the rightmost bit, while the most significant bit is the leftmost bit. If the bit is 1, then the power of 2 it is representing is present, and you add that to the final sum. If it's 0, then you kind of ignore that. And I have a better example on the next slide. So let's take this binary as an example, 1 0 0 1 1 1 0 1. Below, I labeled all of the exponents. As I stated earlier, the rightmost bit is the least significant bit, while the leftmost bit is the most significant bit. And so the exponents are as shown. Yeah, and so the next step we want to take is we want to find where in which positions there's a 1. And so in the 7th position, the 4th position, 3rd position, 2nd position, and 0th position, we have a 1 there. And so we take 2 to that exponent, and then we sum them up. And so what we get is 2 to the 7 plus 2 to the 4 plus 2 to the 3 plus 2 to the 2 plus 2 to the 0, which is 157. Okay, so that is only used to represent positive numbers and also 0, I guess. But what if we want to represent negative numbers? To do so, we want to use 2's complement. And so what 2's complement is it basically takes one of the bits and interprets it as like a sign bit. Is this number going to be positive or is this number going to be negative? And if the sign bit is 0, then you can interpret the number as a normal number that I explained earlier. If it's a 1, then it's negative. And you do some sort of operations to finally get to your final decimal value, which I'll go over in the next slide. So we take this exact same example as earlier, 1 0 0 1 1 1 0 1. We see that the most significant bit, which is the leftmost bit, is a 1. So we know that this number, if we interpret it as a 2's complement number, is going to be negative. Again, about the binary number, it's mainly how you interpret the number. So you can interpret this as an unsigned number or a positive number only, but you can also interpret it as a sign, which means it could be either positive or negative. From a hardware perspective, it doesn't actually make any difference. And so we do the same sort of operations again, except now we interpret the most significant bit as a sign bit. So we take the negative of that rather than the positive of that, and we sum it all together. So we have on the right side, we have 2 to the 4 plus 2 to the 3 plus... Your pen doesn't work. Oh, okay. Okay, anyways, yeah. On the right, we have 2 to the 4 plus 2 to the 3 plus 2 to the 2 plus 2 to the 0, which is the same as usual. But the most significant bit, we take the negative of that. And so what you get is negative 128 plus the remainder. And so you get negative 99 as your final answer for what this binary number represents. Are there any questions on 2's complement and also just normal binary?
Oh, yes, I have one question.
Yeah.
I used to think that the most significant bit, like, it wasn't included in the summation, like, we wouldn't, sum, like, I was thinking we wouldn't sum a negative 120, and I thought like it was only like negative of 16 plus 8 plus 4 plus 1.
No, okay, so that's a great question. That's another way of representing negative numbers. It's not as efficient. So like that's what we call signs magnitude, where the most significant bit is going to be a 0, 1, and that's how you interpret like, is the number going to be positive or negative? And then the remaining bits, it'll determine like the actual like magnitude, right? So if you interpret this number as signs magnitude, then yeah, your thought process is correct, but we usually use 2's complement instead. Does that answer your question? So there are like 2 different ways of interpreting the same exact binary number.
Because we just learned this in M51A today, like I just learned this, and the way he taught it was like like what I was saying, so I just got a bit confused, but yeah, I guess this is a different way of.
Yeah, it's just a different way of interpreting it.
How is the like the unsigned, or I guess like the most significant bit in positive versus like interpreting the sign, like how are those 2 interpretations like equal?
Like they're equal in terms of like when you're computing numbers, it doesn't actually really matter from a hardware perspective that like, is this number going to be unsigned or is this number going to be signed? It's more of like what you think of this number as, like how you use these numbers. Like when you actually build circuits to add or subtract numbers, adding unsigned numbers versus adding signed numbers, it doesn't make a difference. So like they're equal in that sense. Yeah, it's mainly like how you interpret it. Okay. Yeah, so this is the range of a 2's complement 8-bit 2's complement number. As you can see, there's 1 extra bit for the negative number as opposed to the positive number because we have 8 bits of 0 representing 0 as opposed to 8 ones representing -1. And so there is an unbalance, and I just want to stress that because many people forget usually. Yeah, so that was a basic overview of binary and how we can interpret binary numbers. There's a variety of different binary operations that you can make. You could do addition, subtraction. There's also left shift and right shift. So addition and subtraction, you usually do it like how you would do it normally using the decimal system. You add 0 and 1, or you add 2 bits. If both of them are 1, then there's a 1 that gets carried to the next place. And then so on. Subtracting is like a similar vein of thought. Left shifting just means that you're essentially moving the bits to the left. So in this example, when we're left shifting 0, 0, 1, 1, oh no, I haven't. Yeah, okay, thank you. Okay. Yeah. If we're left shifting the 0, 0, 1, 1 by 2, we get 1, 1, 0, 0. And usually when we left shift, we append zeros to the number. And then right shifts, there's 2 different types of right shifts. There's a logical right shift and there's an arithmetic right shift. So the logical right shift, you're moving all the numbers to the right by an X amount, but you're padding the most significant bit with a 0 always. For an arithmetic right shift, this is where when we have 2's complement, when you're right shifting it by like an X amount, you're padding it by what the most significant bit is. And so here, if we have 1, 0, 1, 0, and we right shift it by 1, we pad the number by a 1. However, if we do an arithmetic right shift on 0, 1, 1, 0, then you still pad it with a 0. Because the most significant bit is a 0, not a 1. And you can notice that left shifts, when you do a left shift, it's essentially multiplying by, if you're left shifting by 2, you're multiplying by 4. If you're left shifting by 3, you're essentially multiplying by 8. So you're essentially multiplying by 2 to the X amount. And then on the right shift side, it's kind of like dividing by an X amount. Again, note that there is no multiplication, division, or remainder. However, it is okay to use in lab 1. It's just not very logic and hardware friendly. We usually prefer to use adding, subtracting, left shifts, and right shifts, because multiplication and division, they are very, very costly in terms of logic. And so if we want to perform operations on binary digits of different sizes, so let's just say I have a 4-bit binary, and we want to add it to an 8-bit binary, we want to sign extend it, or basically extend one of the numbers so that it matches the exact same length as the other one. And we call this sign extension, which is basically you repeat the most significant bit X amount until you get to however many bits you want. So here I have a positive number, 0101. If we extend it to 8 bits, then we just have 4 extra zeros on the leftmost side. And this number is the exact same number as this number. For the negative side, when we sign extend it, we add a bunch of 1. And I won't go over why the math, why this works, but the number for this is exactly the same as this. They're both, I think it's -3. Yeah, they're both -3. And finally, it's important to note that when you're conducting operations on binary numbers, it may not be possible to store all the results of the operation in the same exact amount of bits. Let's just say if you want to add an 8-bit number with an 8-bit number, it may not be possible to store the result of that sum in an 8-bit number. And so this is like a general overview. So for addition and subtraction, if you have an n-bit number and you do addition or subtraction on them, then you can very well end up with a result where you have to have n+1 bits to store. Bit shifts, they're going to be the exact same number of bits used. And then multiplication, when you multiply 2 n-bit numbers, you need 2 times n bits to store that amount of information. And yeah, that's just a brief overview of what binary is and what operations you can do with binary. Are there any questions or things I should go over again?
I have a question.
Yeah.
When you do a right shift, like, does the rightmost bit, like, we get rid of it and we pad it with a 0?
Yeah, so in right shifts and left shifts, you essentially get rid of the rightmost bit. It just goes away, and then you pad the left side with zeros or ones, depending on if it's a logical or arithmetic.
It's a left shift, we just get rid of the most significant bit.
Yeah, so like if I have sorry. If you have 1 1 0 0 and you left shift it by 1, then that would just equal to 1 0 0 0.
How will we know whether the right shift is logical or arithmetic?
How do you know if it's going to be logical? Yeah, again, it's like up to interpretability. Like if you want to interpret, like if you want to do a logical shift, then you can append it with zeros only. If you want to perform an arithmetic shift, then you just code it so that it appends the most significant bit.
Yeah, so you're gonna be the one making this logic, so you get to decide if it's logical or arithmetic. But depending on what you're doing, both are useful for their own cases. So you'll kind of just see them as they come.
Yeah.
Yeah.
But which side do we pad on, like, for left shift, we pad on the right side?
Yeah, so for left shifts, you pad on the right side because you're moving everything to the left, and so you have nothing to fill in for the right. And then for the right shifts, you're moving everything to the right, so you have nothing to fill in
So
on the left.
where are the vacancies?
Yes, and you fill that in with zeros or ones. Yeah. These are all great questions. Are there any other questions?
Oh, so if we left shift the right shift by multiple, like if you left shift by 2 and it's arithmetic, like in the top example, it'd be 1 1 1 1.
Are you saying this one? Like this 1010, right shift by 1? Or
If you do an arithmetic right shift by
by like 3, let's just say.
Yeah, then.
Yeah, it would just be all ones. Yeah. Okay. If not, then we're gonna proceed to combinational logic. Yeah.
Alrighty. So let's do this, guys. So what is combinational logic? The jungle temple employs combinational logic to defend its treasure. But how can we solve the puzzle if we don't know what combinational logic is? Well, guess what? You've all already done combinational logic. So the temple uses combinational logic, and even if you don't play Minecraft, you actually did it. Those were the example problems I gave you for the gates. That is actually an example of combinational logic as well. So what it means is that combinational logic is a set of inputs run through wires and gates and produce a set of outputs. So the key point is that outputs are dependent on only the current inputs. So yeah, so what can we do with these combinational circuits? So I'm going to start introducing some actual like logic blocks that are used in like all computers and processors and all that. So the basic building blocks of these combinational circuits are the logic gates from earlier. Um, yeah, I think yeah, everything can be explained with nans and nors. I think I explained why last lecture, but apparently we're gatekeeping it now. So yeah. So now, yeah, now we're gonna go over some circuits composed of these gates, and then eventually we'll basically just abstract the circuit, and then we'll just use the building blocks. And the building blocks we're gonna go over today are the mux and the adders. Yeah, okay. So the multiplexer, the mux, is basically it basically selects a signal from your inputs. So fundamentally, here's an example of a two inputs, one output mux. So it has two inputs and one output. And then there's also a select bit at the bottom here. So these are your inputs. These are the inputs, and these are the this is the select bit. Basically, the select bit will tell you which inputs you want to set as your output. So there'll be like pass here, and then the select picks which one you want. Yeah. So note there's also muxes with like a lot of variety of inputs. You can have like an 8-to-1 mux. So yeah, that's cool. All right. So this is the gate. So this is like the logic block representation of a mux. And on the right is going to be the gate level representation. So really quickly, I'm not really gonna trace through it too much, but you see this Boolean expression at the end, Q equals A S naught plus BS. I didn't really explain Boolean expressions that much, but basically what this means is um, in Boolean expressions, I'll write it down. Why is it tweaking? Boolean expression. Basically, if there are two things next to each other, this means and then if there's a plus B, this means or. Why is my pen so bad? I got a scam one off Amazon because my Apple Pencil died. So yeah. So looking at this, what we're seeing is basically A and S naught, which you can see in this here. And then we also have B and S, which you can see here. And then they're ORed together, which is represented by that plus. So if you want to trace through it and understand the truth table and how it exactly the select bits pick which signal, feel free to do so. It would be useful for your own knowledge. But yeah, I have a quick question for you guys. What programming logic does this work similarly to? Anyone want to take a chance at that? Yes, that is correct. So So as you can see, the mux, it basically has some condition, which can be the select bit. And based off that condition, it will decide what to run. So this can be represented as an if statement, or it could be a switch case. So basically, anytime you're going to code an if statement or a switch case in your Verilog code, it will make a mux. So that's pretty cool. So this is a very important logic block, and it's used in everything. Are there any questions on muxes? Or do you want me to dive deeper in how it actually works, gate level? Sounds good. All right. So now we're going to get into the adders. So, yeah. So the adder basically does what we want, an add. We want to add something. So in our example, we're doing 2 bits plus 2 bits. We're representing that here as the A and B are basically indexed from 0 to 1 and have 2 bits. We also have 2 outputs or kind of outputs. We have the C, which is the carry bit. So that's this. And then we have S, which is going to be our final sum down here. So how do we actually create this using gate logic? We will get into that. So the first thing we need to do is we need to add these 2 ones together. So how do we do this? A lot of times what you'll do in order to create logic is you will create the truth table and then figure out what gates you need in order to do this. Another thing you can do is basically like Boolean algebra, but I'm not covering that. So this is the truth table of how to add. So basically, if you remember, zeros is 0, 0 plus 1 is 1, 1 plus 0 is 1, and then 1 plus 1 is 0 with a carry bit. So that is the truth table that we want to see come out of our logic circuit. So to kind of break this down, basically what we're seeing is 2 inputs and 2 outputs. So we can derive logic for each output to the inputs. So basically, if we focus on the S bit, you see this this relationship between the inputs and outputs. And if you know your stuff, this will look familiar because this is actually the XOR gate. So you can see this was made here. So you see A and B XOR together makes S. And then now if we were to look at output C, so now we're looking at this guy, or not this guy, basically. We see this relationship between inputs and outputs, and we see that is an AND gate. So we know that this is an AND, so basically we have A ANDed with B is going to be our carry bit. So based off this gates, we're able to figure out the log, or we're able to add our numbers together. Yeah, is there any questions on that? Okay, wonderful. So we were able to correctly get this so far. The 1 plus 1 is 0 with a carry bit. However, we need to finish the rest of the operations. So as you can see, the next step is to add the second column, which is going to be 1 plus 0 plus 0. However, this is a little bit different than before because we are going to be adding 3 bits instead of 2 bits. So how do we do this? We use something called a full adder. I don't know if I explicitly said this, but this is a half adder. Oh, yeah, it's right here. Okay, so now we're going to be creating the full adder. This full adder will accept 3 inputs, one being the carry bit from previously, and the other 2 inputs being the inputs, or the 0, 0 in this case. And then you'll get another sum and another carry bit. So, can someone tell me what the sum of these 3 would be? Just shout it out. For this first line. What is the sum?
0,
0. Okay, next one.
1,
1.
1,
1. Next.
0,
0. Next. Okay, keep going. Okay, how about the carry bit?
Zero,
Yep,
zero,
yep,
zero,
yep,
one,
yep,
zero.
yep, 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 yep. Congratulations, you did better than last year, Dazzly. So, so yeah, so that's our truth table for the full adder. Um, so so one interesting thing is that the full adder is actually just basically two half adders created together. So as you can imagine, the half adder added two inputs together, but now we have three inputs. So basically what happens is we're going to add two of them together and then we're going to add the third one to the results of that. So if you actually want to break this down, we actually have one adder here. So if you remember what that looks like, the half adder is just an XOR and an AND gates. So we have our XOR and our AND gates, and we have another adder here, and then we have an OR gate just to put things together. Basically, this OR gate is saying for the carry bit, if two of them or if more than two of them are equal to one, then the carry bit will be one, and if not, it will be zero. So yeah, so that's how you make a full adder. You basically just combine two half adders together, and you're able to add the second column plus its carry bit. Um, are there any questions on that? I'll go through one example. I'm gonna pick this line because it looks fun. So this is zero, this is one, and this is one. Um, XOR for 0, 1 is 1. And then A ANDed with B is 0. So if you remember, basically previously this would be our sum, and this would be our carry bit if we were only having a half adder, but now we want to add C to it. So now we take this sum and we do the same thing with CI. So CI comes here and we do an XOR on it, and XOR of 1, 1 is 0. And then we do the AND gate on it. So that's 1 and 1. So this is 1. And then we can get the carry bit, which is 1. So as you can see, it does work. And it's basically two half adders together. You add A and B, and then you add the carry bit. Any questions? Cool. Wonderful, guys. So yeah, we don't really expect you guys to memorize the circuits. Not really necessary, but it's good practice. And the takeaway is that we can make circuits do tasks like adding numbers and selecting things. So yeah, we'll see how these come together later. Let's see.
Okay, so now let's go back to the original example that Gerard just showed us, where we have two-bit numbers added together. The goal is to add these two together and show the result in S, which is a 3-bit number. And we want to use the digital circuits that we just learned, half adders and full adders, to build this exact adder, 2-bit adder. So let's break it down even further. So let's just look at the least significant bits of both numbers, A0 and B0. What circuit element did we just look at that accepts 2 bits as an input and outputs a sum and a carry bit? Can someone tell me? Yeah, half adder. Now let's look at the second operation. It accepts 3 bits instead of 2, and 1 is the result of the previous bit carry. And so what element should we use here? Yes, full adder. Okay, so now this is the challenge of the lecture. Me and Gerard, we don't want to draw these circuits anymore. So now it's your turn. We'd like you to draw out the block diagram for the adder circuit. You're free to discuss with your neighbors. For like a half adder, just draw like a square, like something like this. and you can just call it like half. For a full adder, you can just have the same thing, but just with a full. And then just be sure to pipe the inputs correctly. We have A0 and we have A1, A0 and B1, B0, and we want to pipe that into the components that we just explained earlier. And I'll give you guys a few minutes to do this. Next slide.
It's just explaining that, and then
Oh,
yeah, you just explain. Oh, and then there's ALU. Okay, I think we might just skip that in the interest of time.
okay.
I think we're slightly behind.
All right, should I skip it? Should I skip it?
Or you can give them some time and then let's go over it.
Okay.
We don't need a big time summary.
I think we're on time.
We're a bit behind because I wanted to start my section at 7, like basically at 7.
7:15.
Okay, yeah, we'll probably just give them like a really short break.
Okay, okay.
I think I can do that.
Okay, okay. Then I'll just
Not many people are discussing, so you can give me a second.
what? I'm gonna start.
I think it's- Or, yeah, you can start.
All right. In the interest of time, I'm just gonna go over the solution right now. Okay, so if you drew something similar to this, then you got it correct. And so I'm gonna break this down real quick. So here we have our first number, A1 and A0. We usually express this in terms of like square brackets and then 1:0. It represents like all of the digits from A0 all the way to A1. And then B, these are our two numbers from here. A0 is this line here, and it gets sent into this half adder. And then A1 gets put into this full adder. B0 gets put into this half adder, and then B1 gets put into this full adder here. And so after you add A0 and B0, it's going to generate a sum, and it's also going to generate a carry bit. And then we pipe the carry bit into the full adder, and then the full adder processes all three of these inputs, generates our S1, and then generates the carry bit, which we can interpret as the final bit of the sum. Are there any questions with this circuit? Okay, if not, that was a brief exercise for adders. And the adder is actually really useful because it's implemented in even larger digital circuits, which we call the ALU. And so the ALUs, or the arithmetic logic unit, is present inside all of your guys' computers, phones, whatever. And what it does is it just processes any information that you give it. So it performs arithmetic operations as well as bitwise operations, like add and subtract, or shifts, bitwise and or. And inside an ALU, there's a bunch of shifters, adders, and multiplexers. And to do more complex operations such as multiplication and divisions, we use something called strength reduction. So I'm not going to go over it too deeply in this lecture. If you're curious, you can ask me after the lecture. But in essence, what you're doing is if we want to multiply a number by 3, we could break this down into binary, which would give us 1 and 1. And then this would represent 2 to the, sorry, not 2 to the 2, 2 to the 1. Oh, oops, it's a big eraser. This is 2 to the 1 and 2 to the 0. And so for this number, we can bit shift x, like if we want to do x times 3, we can bit shift x by, no, left shift. We can left shift x by 1. And then for this number, we can left shift x by 0. And then we sum them together. And that's essentially multiplying the number by 3. And so this is like a more efficient way of doing multiplication. However, you do need to know, like this number needs to be a constant. It can't be like a variable. But that's how we can also do more complex operations. And how we determine which operation the arithmetic logic unit does is through the opcode. It's basically, you can think of it like a series of multiplexes or like a switch statement where it goes through every single opcode. If the current opcode matches that of like add, then the ALU would add A and B. If it matches subtraction, then it would subtract A and B and output the result in S. And this is what you will be making in lab 1. Oh, I already said the answer. I didn't even notice there was a question. But yeah, the question was which digital circuit described earlier allows us to select between different input lines. That I said it earlier is the multiplexer. Basically, you give it the opcode and treat it as like a select bit, and then it will output whatever operation you want it to do. Are there any questions about what the ALU is, what it does, or like how it's implemented?
Is the delay between the input and output signal and an ALU, is that negligible?
No, the delay is not negligible. And I think we'll be going over this in lecture 3, but for now you can treat everything as like instantaneous. But no, there is delay. Oh yeah. Yeah, so the opcode, it's like a series of bits. It could be like, it's usually, I think, at least for, I'm taking computer architecture right now, so we're learning RISC-V, and the opcode is 7. Basically, it's just like a series of zeros and ones, and then that controls like, let's just say if it's all zeros, then the ALU knows it's an add operation. Yeah. Any other questions about the ALU?
Is output part of the instruction, or like is the output, is it just the operation, or does it also include the inputs?
Yeah, okay, this gets a little more into computer architecture, but when you give an instruction, it has an opcode, and then it also has the values that you want to add or subtract or whatever.
Oh, so output is part of the instruction?
Yes, yes.
Okay.
For our sake, you will be basically treating it kind of like another input.
Yeah,
Okay.
yeah.
Yeah.
Okay, if not, we're gonna take a quick break. And we'll be back at
Yeah, 7:15.
7:15.
Yes, if you guys have any questions, feel free to just
Yeah.
shout about it.
The lecture's supposed to 8.
What's up?
The lecture's supposed to end at 8.
Yes.
Okay.
All right, time to get to the fun section, bro.
Oh, how are you gonna?
I'm gonna grill it. I'm gonna switch to my computer. Hey, oh, you have extra pizza?
Yeah, it's not run up there.
Hey, Les, thank you.
Yes.
Like, you just check all the Elvis and all that's all right. We're in the brain, right?
Next week, we talk about it, right?
Yeah.
So what have I missed? What? I did it. Oh.
No,
Like,
no,
Japanese.
so basically like there's a new
Yeah, yeah.
and that is they make you
not in
or like you have to have a
Okay,
subscription.
yeah, no, that was.
What's the
Usually, well, basically what happens
example again?
Okay, this is not covered in FFV one, but it's just like a more efficient way of doing multiplication when you know like one of the numbers. Oh, sorry. When you know one of the numbers.
But I think
So let's just say we want to do
but there's usually a font
1010
organizations can use.
times.
Well, apparently we exhausted a bunch already.
Like this is 5 times.
But unfortunately,
So what you can do is
I think it might be.
rather than actually doing the multiplication, which is very costly, we didn't go over it.
I think it's.
but
I think
you have to do it. Oh, that's you have to do like how you do the other way. Like 0, 1,
Yeah, I'll just have to because like. Yeah.
And
What's the so the leftmost?
Oh really?
I can't actually.
yeah.
Like, this is.
Yeah, it's been kind of annoying.
This is a 4.
Like in other
2, 1, 0. Because this is exponent
Yeah. Sometimes.
Oh, sorry,
Sometimes it's
sorry.
just left open.
Yeah. 4, 2.
They crack down.
So this is from.
Yeah, this
Just
is.
remember that like this is the
No, this is
exponent
like.
0 position.
I truly support the trend.
So how is this?
It was like. Basically,
Sorry,
like,
I made a mistake.
he's doing it. Like, he used to be an IEEE officer.
That's his.
Yeah, this is his. Yeah, I know, right?
And so what you
Negative versus positive.
Really?
You got
Could I actually lab? Yeah, that was heavy.
okay,
I
yeah,
worked
back to
out
this.
the-
If you want to do 5 times 3,
Juggling.
rather than like
Juggling
doing
all
all
of
of
them.
them, what you can do is you can find whichever bit is 1 and you do a bit shift. So bit shift actually does not
I think
make
that's
you
just
like
like
that. You'll learn this in security.
Yeah.
You want to shift this by 1?
Yeah, I
You
just
essentially add a
figured
0 here. And then, so this is,
I sure hope so. It's a
and then
bit
this one is
sensitive.
by 0. And so you get 0, 0, 1. And when you add them together, you get the exact same answer as. And so this would be, what did I do wrong? Oh, sorry. Yeah, this is.
And like. I mean, maybe I should just look at our dollars. What if I want to multiply by 4 instead?
Yeah, if you want to multiply by 4 instead, then this number would be 0, 1, 0, 0. And then you just bit shift by 2, this number, and the result would just.
All right, we're recording. Let's go, guys. All right. Honestly, oh, okay. Honestly, if it's a little purple, I don't think it's as bad for this. So, all right, now we're gonna get to other stuff. I couldn't come up with a title because I'm going to be covering a lot. Likely, I'm just going to be staring at my computer. So if you, what? The microphone's on my iPad. Yeah. Okay, so yeah, so we're going to go over this stuff. So basically, I'm gonna run through a Vivado project, start to finish, and we'll get through that. Okay, let's begin. All right. So the problem, what are we gonna do? We're going to synthesize a 2-input mux from the gate level with an LED indicating output. That sounds pretty cool, but it's like 2 lines of code. So we're going to create the same behavior as well using an if statement and observe how this gets synthesized. All right. So this is just a quick depiction, just a reminder. That's what the gate level looks like, and that's what we're going to be making. Alrighty. So quickly, a quick note on system Verilog. So kind of like your, this is blocking. All right, so kind of like your C++ header files and main and etc. There is a module hierarchy. This is what we call our files. We call them modules. Yeah. So basically there's also a top file. So I'm gonna explain all this real quick. So basically there are kind of 3 subdivisions of file types that you can have. The first one are design sources. So you'll probably have one that like encapsulates everything, kind of like your main, and then you'll have modules underneath it. And those modules can have some modules if you want. You can have as many of those as you want, and we'll show you how they connect together. And then we also have simulation modules. So these are called test benches. We won't really be teaching you how to make test benches today. We don't have time for that, but I'll show you how to run one that I made for you guys. Basically, lab one, I wrote you a test bench, just run it, and you can see if you did it correctly. And then we have constraints. So the constraint file is basically your pinouts. So how it tells the code what variables map to what pins on the FPGA. So this is how you get the code related to your hardware. Yeah, so those are the three file types. Yeah. Oh, there's also the top file. So basically when you're making or going through a Vivado project, it'll probably make more sense as I show examples. But the top file is basically the module that you select to be your top. So basically when you're running either like a synthesis or an implementation, that top file is going to be the one that's going to be focused on. You'll see it in action. Alrighty, so really quick, wires versus registers and versus logic. This might be a little confusing, but stay with me now. So system Verilog is a VHDL. So what does that mean? It's a hardware description language. So we're talking about hardware here. So you can kind of think of your data types as hardware. Now this isn't really true, because system Verilog is, you can think of system Verilog as basically C++ and Verilog as C. So in Verilog, it's all completely hardware, but in system Verilog, it's a little bit simpler. But it's kind of still useful to think of things in hardware because that's what we're trying to make. So quick dive into computer architecture. We're going to be mostly just looking at wires and regs real quick. So wires are basically, you can think of them as wires. So you connect two things together. When one thing changes, the other will change. They're completely related, completely assigned. They're basically aliases. They're the same thing. And then there's regs. So regs are basically registers. So if you know some computer architecture, there's basically different memories. So register is one of them. There's also RAM. There's also like DRAM, all those things. But basically, registers are the fastest memory access you can have, and it's typically what is used when you're actually like running a program. So when you like create a variable, those are typically stored in registers. So yeah, reg is register. That's kind of it, and then I'll explain what logic is. So these three are going to be, these three are going to be the data types of system Verilog. So you either say this is a wire, this is a reg, or this is logic. So when do you use what? So basically wires, they reflect the driver. So what I meant is like, the driver is whatever you're setting the wire equal to. So if you set A equal to B, anytime B changes, A will be changed as well. So they're assigned together. There's also multiple drivers. So basically, don't worry about that too much, but it can do it, but it's really weird. So don't do it, but that's the thing. There's continuous only. So what this means is assignment. So we're gonna see two different types of assignment, procedural and continuous. Continuous basically means it's always going to be equal to each other, while procedural means like you have to do some procedure. So if this happens, then this. There's like a for loop, there's logic behind it, the assignment. So like if you have to do this is equal to A plus B, that is a procedural assignment. Or if it's an if statement, it's a procedural assignment. But if you're just like straight up this equals this at all times, it's continuous. So wires are only continuous, and wires are the only data type that are used in gate level designs. You can't use logic for them. So the next thing is registers. So registers are wonderful, but as a data type in system Verilog, don't use them. Basically, logic is just a better version of registers. So what is logic? So logic is a data type that system Verilog made up that basically streamlines this whole thing. Basically says you can nearly use logic for everything. So the main reason to use wire is that it's used for gate level designs, but basically for everything else, you can use logic. So logic can be used for continuous and procedural assignment. It can be used as inputs, it can be used as outputs, it can be as flexible synthesis. So what this means is logic is not a hardware type, as you may be able to tell because I didn't mention it earlier. But basically what it does is when the Vivado synthesizes this, it's going to see logic, and it's gonna see how you use the logic, and it'll figure out what's the best hardware for it. Whether that's a reg, that's a wire, or a latch, which you guys will learn some other time. So basically, when in doubt, use logic. But yeah, those are the data types. There's also inputs and outputs. So when you're making modules, you're obviously gonna have some kind of input and some kind of output. If you don't specify which data type, it will default to wires. So that's just something to note. You'll see examples of it as I go through. So basically, when you are describing a register, things are indexed like 4 to 0. As Jonathan mentioned earlier, basically that means is 4 is the most significant bit, and then 0 is the least significant bit. Like it's a little weird because typically you'll see 0 to 4, but we're indexing it 4 to 0. And this is because the most significant bit is on the leftmost side. And typically it's easier to think of the most significant bit being the higher index number. So that's just typical formatting. So when we declare register sizes and logic sizes, we'll represent it like this. These sizes are basically how many bits you want it to be. So if you want a 32-bit number, you do 31 to 0. And if you want like a 40-bit number, you do like 39 to 0 and so on. So yeah, if you just have a 1-bit number, you don't even have to specify the size. So you can kind of think of it as an array. And the array is like bits. Alrighty, so the rest of this stuff I didn't make slides for. So you're gonna have to watch lecture back if you want to, or just take notes. So now I'm going to actually open up Vivado and we're going to make a project. So let's do that. Vivado. So open up Vivado. Hello. Oh, no, don't leave, don't leave. Is it opening? Oh, it's because I'm low on battery. My shit's slow. No, I can just connect the extender. Okay, there we go. It's popped up. Okay, so hopefully you guys have all managed to install Vivado by now. So if you want, you can follow along, but you don't have to. So basically, this is going to be the opening page. So here we're going to create project. We'll go ahead and click next. You will name it something. Sure, project 2 sounds cool to me. And then you're going to select the project type. So our project type is RTL. Nice. So in this section, you can add any imported sources if you'd like. You can do and constraints, but you don't have to. And then you can always import later if you need to. So I usually don't do anything here. So this part, we will now be looking at the boards. So we want to select our board. So in here, our board name is basis 3. So in the search, just look up basis 3, find it, click it, and click next.
If you don't have it, click the refresh button on the bottom left.
Yeah, so Jonathan's saying there's refresh button. It might help you out if you're struggling to find it. So next and finish project. So you can see our board here. You can see the FPGA. So yeah, so finish project. Alrighty, guys. So quick run through of the IDE. On the left side, we have the project or the flow navigator. Flash project manager. So yeah. So System Verilog has multiple steps, not just compiling and running while you're going through the code. So we're going to kind of explain each one. Here we have IP integrator. This is something we won't really touch, but I did say I might make an extra lecture on it if you want. And then we also have simulation. So simulation basically means is you're going to give the program inputs and outputs, and you will see all the outputs. And this will be run locally on your computer, not on your FPGA. This just lets you test everything ahead of time and really distinctly analyze what's going on and helps you make sure all your logic is correct. Next, we have the linter and analysis, RTL analysis with running linter. This is just basically compilation, so compiling your code. You can see that a lot of these have reports in them. The only thing, there's a lot of cool stuff here that like you can use to make sure everything's working properly. The only thing I'm really going to make you guys look at is the schematic. So what the schematic is it will basically translate your code into digital logic design. So the like block diagrams that we showed earlier. So yeah, hopefully that'll be pretty cool. Next thing is synthesis. So synthesis basically will map your system Verilog code into a digital circuit on the FPGA. So it'll describe what are the lookup tables and it'll map your pins and such. So after you run the synthesis, you can do your pinout. And then we have implementation. So this will basically map onto your FPGA. So actually where are things located? What is the routing between the lookup tables and all this? And then finally, we will go ahead and generate a bit stream, which is basically what we're actually going to send to our board. And then the board will understand how to map itself. And then we'll open up our hardware manager and we'll send it over. So in this middle area, we have this sources tab. In the sources tab, mostly you'll be looking at the hierarchies. You can see we have design sources, constraints, and simulation, which I kind of explained. You don't really have to worry about utility. Yeah, so this is where you're gonna be putting all your files, and then this properties tab, you can just kind of get rid of it. It's kind of useless. And then at the bottom, you have a bunch of tabs. So this is the console. So basically this console you'll see test bench outputs here, and you'll see any errors. You can also look at errors in the messages tab. So yeah, that's kind of how you'll like debug things. And then here's project summary, but this is also, once we start opening files, this is where the files will start opening up. So to begin, we want to create our first design source. So you can click on this plus sign and you can pick which source you want to make, constraints, design, or simulation. So we first need to design something, so we're going to go with design sources. Alrighty. So I did add design source, and now we create the file. Oh wait, I need to name it. Oh wait, it's not the name yet. So I create file, and then I want to make sure I select system Verilog, and our file name, I'm just going to call it mux gate level. So quick note, since I wrote you guys a test bench in lab 1, it's pretty important that you stick to the naming conventions I set. If it doesn't work right away when you run it, just let me or Jonathan know and we'll fix it up for you. But if you stick to the naming conventions, the test bench should just be plug and play. So after system Verilog and naming, you can click OK and you can finish. So now here you can add your inputs and outputs, but I kind of just like typing it because I don't like this IDE. So I'm just going to click OK. And yes. So you can see now it was created in our design sources tab, and we can open this up. Yeah, so now we have this. This is our basics. So this thing here, this timescale is basically only useful for simulation sources. So you can just kind of get rid of it. And we'll kind of explain what it does later. But yeah. So the first thing we need to do is to set my inputs and outputs. So these will be the parameters for our module. So right now we're trying to make a mux on the gate level. So if I alt tab over to lecture, so this is what we're trying to make. So as you can see, we have 3 inputs. So this is A, B, and S, and we're going to have 1 output Q. So I'm going to go ahead and do that. So in order to define your inputs and outputs, you are going to type it in the module parameters. So you can see here, so you can just type input A, you can go input B, you can go input S, and you go output Q. So since I'm going to be doing this on the gate level, I did not define the data type, which means it's default to wires, because wires are the only thing for gate level, but don't think you guys will be doing much gate level design. So yeah. As you can see, I already said that. So now that looking at what we need to make first, so looking at here, the first thing I would do stepwise is I would create an S knot. So what I can do to create S knot is I can create a new wire and name it knot S. And I can write the logic for that, which is going to be not some kind of name. So knot is the operation, and then this U1 is our name. What U1 typically stands for is unit one. I think you can just name it anything, but typically in System Verilog, people call things by units, so I'm just gonna call it unit one. And then the first parameter is going to be what we're setting, and then the second parameter is the first parameter is gonna be our output, and the second parameter is going to be our input. So as you can see, we have a NOT gate, we're inputting S, and then we're outputting not S. So that's what that code does, and you need semicolons.
Sorry, could you expand that window?
Yeah, sure. So I don't know if I can zoom in. Does that make it any clearer? Is there a zoom option? Uh, Not sure. Oh, also my Zoom session's blocking a lot. It's okay. Yeah, sorry, I don't really know if I can make it any bigger. Is it hard to see? Okay. You know how to make it bigger? It's not working. Yeah, it doesn't zoom in. Yeah, it doesn't zoom in.
That's the biggest.
Yeah.
Maybe just write out a text file.
I'm not writing on text file. Yeah, zoom in. There seems not to be a zoom function. Uh, yeah, that's quite unfortunate. Um, does not seem to be. Yeah, I don't know. They don't seem to have zooming in Vivado, which is unfortunate. If you want to get closer, you can. But fortunately, this is what we'll have to do with. So yeah, I made this not S wire, and then I set the not S wire into a NOT gate with the input being S and the output being not S. So now we have not S. So the next thing in our design is we need to put an AND gate on this not S and this A. So simply I do AND, I'll call it U2. So the first one is our output. So our output, I'm just going to create another wire and just call it temp1. And then, so our output is going to be temp1, and then our inputs are going to be not S, and it's going to be A. And then the next thing we need to do is make an AND gate for B and S. So same thing, and U3. I'm going to make a temp2. I'm going to do S and A. And there we go. And then I'll do a wire, and then this will be temp2. And the final step is going to be to OR our two results. So it's going to be OR U4, temp, or it's going to be our output, so that's Q, and then it's going to be temp1 and temp2 inside. That is really hard to see. Yeah, quite unfortunate. Sorry if you have to strain your eyes a little bit, but yeah, basically, you can see there's 4 gates here. I created 4 gates. I put the right inputs and outputs, and I made all the wires I needed to. Oh, semicolon. Oh, parentheses. Okay, so this is basically how I created my gate level mux. This is all recorded, so if it's hard to see, you can watch the recording over. But yeah. So I made my gate level mux. Now I need to make sure the code is ready to go and good. So if you remember, the run linter in RTL analysis is basically compiling your code. So I'm going to run linter. So there were no violations found. Let's go. We did it. So one thing I wanted to mention is that, so now that we made sure it works, I can open up the elaborated design. So I'll save, open up the elaborated design. So what this does is it'll allow me to see the results of the linter, and part of those results is the schematic. So from this code I made, we'll be able to see what was produced. So as you can see, this is the schematic. And if I alt tab, yeah, it's exactly the same. This here represents the NOT gate, but other than that, it's exactly the same. So we were able to create the logic. So now that that looks all good, are there any other questions other than like not being able to see it? So yeah. So the next step, I'm able to see the digital logic and I wrote my code, but now I really want to make sure it works. So I'm going to exit out of the elaborated design.
Oh, I have a quick question.
Yeah, go for it.
Why are there like those little dots hovering above the output of Zans?
Great question. Oh, that's the
Like, because that's not Zans, right?
Yeah, great question. So basically most of the basically everything is better. Things are more efficient if it's NAND or NOR. So long story short, all these gates are made up of transistors, and NAND and NOR gates, or anything like not XOR, NAND, NOR, there are less transistors than and OR gates. So typically hardware will try to synthesize everything as NAND and NOR. So this little NOT is not added in the path because it's not actually a NOT gate, but it's basically saying this is like a NAND with a NOT to make AND. Because in reality, that's what you have to do in hardware. An AND gate is actually made by doing a NAND gate and a NOT.
Oh, so it just signifies that like the way that
Huh?
you present that is like.
I don't think so.
But like, that's still a, for our purposes.
Oh, wait, you might be right. Okay, never mind. I'm actually tweaking. I'm explaining too much. I went too deep into it. But basically, this just means output.
It just says O.
It's just O for output.
All right, great.
Yeah, okay. Yeah, okay. All right, so now that we saw the schematic, we saw it looked like what we want it to look like. We can actually verify how it works. So since you guys won't be writing test benches, this is exactly what you will be doing. So we want to simulate this. So I have a simulation ready. So I'm just going to go ahead and add a source. So I have a simulation source I want to add that's ready to go. So I'm going to add a file. So if so now I'm going to look for where I put it. Oh my God. What did I name this thing? Lab 2? Lab Oh, lecture 2, that's why I named it. Okay, yeah. So it won't be, you won't have to go through all these files. I put it in a nice spot for you guys in lab 1. What the heck? Lesson sources. Okay, so I imported this test bench. This is what you guys will do for lab 1. So import the test bench and finish. So now if I look back at my sources tab, we see under simulations, we have this new test bench, TB. And as you can see, it actually made things so you can actually see the hierarchy because TB uses the thing I just made. So you can see it like that. So now I want to run this simulation. So how do I do that? Just right click it and set it as top. It automatically did it because it recognized that it's using something. So it's always good to check, make sure that the thing you want to do is set as top. So now that it is top, I'm going to run simulation, run behavioral simulation. And it's running. All right, so there's a whole bunch of things that you could check for, but to make this easier, everything will be printed out in the console. So as you can see here, it shows all the inputs. Hopefully you can see there. It shows the inputs and the resulting output. So as you can see, with select bit 0, and then AB0, it outputs 0. And then with A equals 1, B equals 0, and select bit equals 0. So basically it's meaning the output is equal to A. It sets the output equal to 1 since A is equal to 1. So I can look through my results and verify that everything there is correct as it should be. So after the simulation, I'm now confident I successfully made a MUX. So the next thing I want to do, I can close the simulation, is I wanted to show you implementing a MUX as an if statement. So we'll kind of follow the same steps. So I want to create a new design source. So the design source, if you remember, I create file, I set it to system verilog, and I name it something. This one, I'm going to name it MUX if. Click OK, finish. And I'll write my inputs and outputs. So under design sources, you'll see pop up our next module. So it's not a simulation source, so I can just delete that. And then we can start. So this if module will have the same inputs and out. Oh, that's our test bench. So they'll have the same inputs and outputs basically. So I'll just copy paste them. So for this one, let's see. Where was I? So truth be told, we won't really be doing as much gate level design. We'll be mostly working on the logic level. So in order to write logic, basically things will happen under certain conditions. So how you control these conditions is in blocks. So basically, any logic that you're going to write is going to be in an always calm block. So I'll kind of explain that a little bit better. One thing to note also is that this is what you'd call a continuous assignment. So this is constant, while anything made inside this block is procedural. So basically what that means is inside this block, the procedure will happen only under certain conditions. But in this block, this is continuous, so this always occurs. So going back to this, in this always calm, basically what this means is you'll see other always blocks, but basically what it means is that under this, if something changes, you will run the code. So in always calm, it basically means if any inputs change, then your output will change, which is basically what combination says. It says that all your outputs are directly related to your current inputs. So anytime an input will change, this block will run. So in this block, if you remember, wires cannot be used in procedural assignment. So I need to make all these inputs and outputs into logic. So now we're going to be working with logic instead of wires. So in this always calm begin, we can go ahead and do our logic. So basically, so how the mux works is if select bit is equal to 1 bit. So basically, inside of system Verilog, a lot of times you'll be working with bits instead of decimals. So it's always good to cast your numbers as either bits or decimals. So basically, right there I put 1 bit 0. So the S has 1 bit of value and that value is 0. So in this if statement, I want it so if my select bit is 0, then that means our output is going to be equal to A. And then if else, so that means if our select bit is equal to 1, that means our output will be equal to B. Yeah, and that's pretty much it. That's pretty much the logic of a mux. If our select bit is 0, output is A. If our select bit is 1, then our output is B. And that should be ready to go. So now that our code is ready, I can go ahead and compile it. Oh, I actually made a mistake there. So always remember the thing that you're interested in, set it as your top. So I'm setting my if as top. So now I compile it. And now that it's compiled, I can look at the schematic. So you see here, the schematic actually generated a mux. So out of that if statement that we wrote, it created a mux that has a select bit S, has inputs A and B, and it has output Q. So that's pretty cool. We've created our code and we see what it actually ends up in digital logic. So we were able to do what we wanted, which is great. I'm going to skip simulating this one, just out of the interest of time. And now that the logic is ready, I'm going to create my main module. My top module is what it's usually called. And yeah. So in the top module, I'm going to create a new design source. I'm going to make this system Verilog. I'm going to call this mux top. Alrighty, so this mux top, let me open it up and close my design. So in mux top, we're going to have the same inputs and outputs again. So I'm just going to paste it again. But basically the point of this module is low-key kind of useless for our example, but I'm showing it because it will be useful for you guys. In this module, you're basically going to want to instantiate all the modules that you made, and you're going to connect them together. So for example, I'm going to instantiate the if mux. So I'm going to do mux if. I'm going to name it design under test 1, which is kind of bad naming, but it's okay. And then basically you're going to map parameters from the top module into the parameters of the if. And it just so happens I copy pasted it, so they're named the same. So basically what you do is you do this. So what this means is that parameter A in the mux will map to A in the top module. So that's how you kind of connect the two. And then I'll do the same for the rest of my things. Oh, that's S. Alrighty, so now we have successfully mapped our mux to our top module. So what next? So I'm going to go ahead and compile this and forget to run it as top again. Yeah, so now this is our top module. So I'm going to set that to top. I'm going to go ahead and compile it. And we had no violations. Wonderful. So now I'm going to go ahead and run synthesis. So quick note, when you run synthesis, this can take a long time. Oh, shoot. There's an error. These need to be logic. Okay. So, what? While I'm debugging this, basically what I was saying is that synthesis can take a while. I think my final game took like 10 minutes to synthesize. So like our case, this is a pretty small program, so it should only take like a minute. You can see your synthesis progress here. Yeah, it's running, it's synthesizing. It's just like it's like really powerful and it does a lot. Like mapping an entire FPGA is a lot of work, so it takes a while sometimes. I think my final game for reference like pretty much used every single register, so 10 minutes is like your max. So you don't have to worry about it too bad. But yeah, so my synthesis is complete. So I'm going to open my synthesized design really quickly. And basically, in the synthesized design, you'll see this. You don't need to worry about this, but you'll see this IO ports pop up in the bottom. So in here, you'll see all of your inputs and outputs, and now you'll need to map these to pins. So what you can do, okay, I'm not leaking anything. Ooh. Where's actually? Okay, so you can go to dev links. You can find this link. This link will give you all the pinouts. So basically what I want to do is map my inputs to switches and my output to an LED. So you can see here, these are the switch numbers, and my LED is going to be U16. So I can go ahead and find my A. So I want this to be a switch. So switch 0 is V16, or sorry, V17. Switch 1 is V16. Q is going to be W16. And then the last one is going to be W17. So now all of my variables have an input or output pin. So one thing to note is you do need to set the standard. So the standard for our board is LVCMOS 3.3. And then you need to set that for every single pin, pretty much no matter what pin you choose, that's what our board standard is. So yeah, so now I've successfully mapped my variables into inputs and outputs. And now I can just click save. So I click Control S and I'm saving it. And now that it recognizes that there are pinouts, it will automatically generate my constraint file. So I'm just going to name it constraint, click OK. And if I go to sources, I'll see in constraints, it now created this constraint file automatically. So that's kind of how you do your pin mapping to your FPGA. All right, so we're pretty much there. Basically, after synthesis, you can just go straight to generate bitstream. There's nothing you need to do after implementation, so you can just run them at the same time. If you go straight to bitstream, it'll run implementation, and then it'll run the bitstream. So yeah, so now what we're going to do is we're going to put it on our FPGA. Where's my FPGA? All righty. So the FPGA, plug in the micro USB, plug it into your computer. Ugh. Where's my USB? Almost done, gang. All right. So it's finishing up the bitstream and the design. One thing to note is when you're using the FPGA, there is an on switch. There have been multiple times where I've been staring at my FPGA wondering why it's not working, and it's because I didn't turn it on. So turn it on, it'll light up. It's routing the design right now. It's taking a second. Any questions while we're waiting? Cool. 5 more minutes, guys. All right. So now, after the bitstream was created, we can open the hardware manager. So the hardware manager opens. I click open target and auto connect. This will basically find my board. All right, so my board was found. It is this guy right here. I can click program device. And now it's sent to my board. So what is the logic behind this? I think it's working. There's things lining up. So yeah, that's pretty much end to end how you do a Vivado project. It'll probably be useful to just watch this as you're doing lab 1. So yeah. Holy. What the? All right, back to the lecture. Yeah, that's it. Thank you guys for listening. Thanks for coming. If you have any questions, feel free. Yeah.
So this is what I have so far, but whenever I try like doing something, it wasn't like
So currently, you write inputs before your every single one of them. So before B and before C also. So right now it's C and B and it doesn't know.
okay, so then again,
So C and the so got A, so that input you get rid of the first one. So you write input B and you can
each on their own line.
Yeah.
Oh, okay, so otherwise, is it fine like the rest? Like the rest of the one?
Okay.
Like this? Winter's like the compiler, right? Like it just checks. Yeah, I wasn't able to like completely follow everything, so is there like
Yeah, I was running it super fast. Don't worry about it. This is all recorded and I'll post it. So
okay.
I have to bring it back as well.
okay, let me make sure I stop.
Yeah.
Oh yeah. Wait. Oh, I didn't stop the recording. Let me stop the recording.